Hello everyone, we are now on Module 6, Stress Distribution in Soil. Before we discuss the concept and principles, let us try to identify the learning outcomes for this chapter. So, at the end of this module, the students are expected to recall normal and shear stresses and the Mohr circles method of determining stresses on a plane, identify stresses caused by a point load, determine vertical stresses caused by vertical line loads, determine vertical stresses caused by horizontal line. Determine vertical stresses caused by a vertical strip load of finite width and infinite width. Determine vertical stresses caused by a linearly increasing vertical strip load of infinite width. Determine vertical stresses caused by embankment loading. Determine vertical stresses caused by a uniform circular loads. Determine vertical stress caused by a uniform rectangular load. So basically, when we talk about stress distribution, that is the stress that is caused by a certain load that is being applied on a certain area. So when the structure is constructed on the ground, the self-weight of the live load imposed over structure are transmitted to the foundation. So we have to bear in mind that soil are also subjected to stress due to the load it carries from the superstructure. When we talk about superstructure, that is the structure that is above the ground surface. So the load transmitted to the foundation is directly transferred to the ground through the foundation of the structure. This load transferred by the foundation applies the effort on the soil. The effort induces stresses in the soil. The distribution of these stresses is known as soil distribution. So the soil stress distribution affects the stability and safety of the structure. So you have to take note that the soil stress distribution, it has an impact. So meaning to say it affects directly the stability and safety of the structure. So the factors that affect the soil stress distribution are, number one, you have the characteristic of the load. 2, geometric specification of the foundation. You have 3, attributes of the loads of the soil. And 4, the method opted for the computation of the stresses. So the construction of a foundation causes changes in the stress, usually a net stress. The net stress increase in the soil depends on the load per unit area to which the foundation is subjected, the depth below the foundation on which the stress estimation is decided, and other factors. So it is necessary to estimate the net increase of vertical stress in soil that occurs as a result of the construction of a foundation so that settlement can be calculated. So basically, this chapter discusses the principles of the estimation of the vertical stress in soil that is caused by various types of loading. So based on the theory of elasticity. So basically, this would include determination of the normal stress on an inclined plane with known stresses in two-dimensional stress element, determination of the vertical stress increase at a certain depth due to the application of load on the surface. The loading type includes the point load, you have the line load, uniformly distributed vertical strip load, linearly increasing vertical loading on a strip, embankment type of loading, uniformly loaded circular area, and uniformly loaded rectangular area. Although natural soil deposits in most cases are not fully elastic, isotropic, or homogeneous materials, calculation for estimating increases in vertical stress yield fairly good result for practical work. So, as mentioned, we move on now to normal and shear stresses on a plane. So, this particular section will be a review from your strength of materials or mechanics of materials. So, as you have observed, based on the figure, you have a soil element with normal and shear stresses acting on our free body diagram. So basically, you have the stresses in the x and y direction that is used to find the normal and tangential stresses for any angle. So you have here our stresses in the x and of course in the y direction. So This can be used to identify our normal stress. The stresses in the x and y direction can be used to solve for the normal and tangential stresses for a given angle. So, based on our discussion before, we have learned that normal stress would be equal to this equation and our tangential stress equal to this equation. So basically, these are the stress on the y direction, stress on the x direction, and theta is, from this figure, this is our theta. We simply have to get that angle so that it can be substituted to this equation so that we can find for the normal stress and the tangential stress. So on this particular figure, you have to take note that this is our tangential stress and this is our normal stress. So basically, our normal stress is acting normal, perpendicular to our plane. So we have, of course, we learned about principal stresses. So the value of theta such that our tangential stress equal to 0 would be given by this equation. So by using the value, we can find our principal stresses. So our major principal stress is equal to, basically that is sigma sub 1, which is equal to this expression, and our minor principal stress, which is our sigma sub 3, that is equivalent to this equation. So if you're going to have the Mohr circle, based on this Mohr circle, we have identified before, we have learned how to plot our stresses. So basically, we plot our our major principal stress and our minor principal stress. So from here, this is our minor principal stress, which is denoted by sigma sub 3, and our major principal stress is sigma sub 1. You simply have to identify each value, then try to plot on our figure, then basically how to have a Mohr circle, having the value of sigma sub 1 and sigma sub 3, you get its center, use a so that you can have a perfect circle here. You try to connect the points of sigma sub 1 and sigma sub 3 using a protractor. So you can draw your Mohr circle. So the Mohr circle may be used instead to find the normal and shear stresses acting on a plane. So basically for this, the radius of the circle is given by this expression. So that is the square root of sigma sub y minus sigma sub x all over 2 raised to the second plus tau sigma sub x squared. So this is the radius basically once you have the values for stresses along x and y direction. So the stresses on the x and y direction of the plane are plotted. So you have here you're going to plot your stresses along x and y plane. So the stress on a plane EF may be determined by rotating an angle theta or 2 theta, where theta is the angle EF makes with AB. The coordinates of the point reached gives the stress on plane EF. So basically, this one illustrates our stresses. We have, of course, we have an angle theta which makes with the line AB. So from this illustration, our 2 theta is this one. So we have our 2 theta. So this illustrates our 2 theta, which makes with the line RM, with the plane RM and plane line OQ. So point R, point M, they have the respective value for stresses along normal stress and your tangential stress. So this is your shear stress. Basically, this R and M and actually our Q, they have their normal stress and their shear stresses. So once you obtain the value for your normal stress and your shear stress, you can plot the points. For example, for this, you have point R, point M, and point Q. So we have here a sample problem. A soil element shown in this figure. The magnitude of stresses are sigmas of 2, 120, sigmas of x 120 kilonewton per meter squared, tau is 40 kilonewton per meter squared, sigmas of y is 300 kilonewton per meter squared, and theta is equal to 20 degrees. We're going to determine the magnitude of the principal stresses and the normal and shear stresses on plane AB. So for this one, you have your illustration for our stresses. It acts on our soil element. So we are given with the magnitude of the stresses and of course as well as the angle theta, which is 20 degrees. So we're going to determine our principal stress and the normal and shear stress on plane AB. This is our plane AB on our soil element. Makes an angle of theta 20 degrees with the horizontal. So of course, major and minor principal stress denoted by sigma sub 1 and sigma sub 3. Using the equation that was presented a while ago to compute for sigma sub 1, substitute the given value for the stresses x and y direction. You get the value for sigma sub 1, which is the major principal stress is 308.5 kilonewton per meter squared, and the minor principal stress, again using the equation that was presented a while ago, sigma sub 3 is equivalent now to 111.5 kilonewton per meter squared. And we are going to compute for the normal stress and the shear stress. So the normal stress is equivalent to this equation. So you simply have to substitute our sigma sub 1, our sigma sub x and sigma sub y to this equation, of course our theta. So when you try to simplify, it gives us this value, 233.23 kilonewton per meter squared. This is now our normal stress. For our shear stress, this is the equation. You get substitute the value for sigma sub y, sigma sub x, as well as the value for theta. And the shear stress is equivalent to 88.40 kilonewton per meter squared. So we have solved now our unknown data for sample number 1. So we move on now to stresses caused by a point load. So when you talk about a point load, it is an equivalent load applied to a single point, which you can determine by calculating the total load over the object's surface or length and attributing the entire load to its center. So the load applied from the column, wheel, or machine, those are examples of a point load. Basically, a point load is a point load because it is effect in a point. So we have here an illustration for a point load. So basically for this, we use the concept of Bosinic, which he produces or he studied during the 1883. We solve the problems of stresses produced at any point in homogeneous elastic and isotropic medium as a result of a point load applied on the surface of infinitely large half space. So this is the figure as illustrated by Bosinic, solution for a normal stresses at a point caused by a point load P.